Hey, welcome back to Calculus. We're going to look at some more examples on hydrostatic force from section 8.3 in this video lecture. No new ideas, just more examples. And what I want to emphasize is, how to take an example as it's stated, say, in the text, and choose a coordinate system that facilitates computing that integral. What do I mean choose a coordinate system? I mean, you guys have been doing these. Hydrostatic force depends on depth. And if the shape is not a rectangle, the width at a given depth might also depend on that depth. So you basically choosing a coordinate system means you're defining some variable, and that variable determines these quantities we need to know, that depth and that width. Okay, so let's take a look at an example. I would stop the video here and try to do this example yourself. I mean, I'm going to kind of read through it and then quickly scroll down and show you how I would coordinatize this problem. But I think you'll get more out of this if you, at least for 5 minutes, 10 minutes, stop the video and try to do this yourself. You can probably do it, no problem. So what's the example about? It's about a trough, yeah, and it's filled with some liquid. It's not water because it has a mass density that's slightly less than water, but we don't really care about that. It's given. And then the ends of this trough are equilateral triangles, and they're pretty big. Their side lengths are 8 meters long, and they're oriented so that one of the vertices of the triangle is at the bottom. That's a lot to visualize right there. I hope you'll stop the video and kind of try to visualize some of that stuff. And we want to find the hydrostatic force on one of those triangular sides. All right, so pause, try to do this problem. Good, you're back. I'm going to scroll. This is how I visualize that trough. It's just a triangular prism. It's got triangular ends that are 8 meters in length, and the vertex is at the bottom. So we want to calculate, the problem asks us to calculate the hydrostatic force on one of these triangular sides. All right, so we need to coordinatize that problem. I'm going to, you could do this in the 3-dimensional picture, but I think it'll get a little busy and I want to make it a little bigger. I'm going to just copy that triangle and move it over here. I want to make it a little bigger. My software is not going to let me do this in a pretty way, but let me sort of try to make this thing look equilateral. I apologize if it's not perfect, but we don't need it to be perfect. It's just schematic. So I'll just label the side lengths. It's 8. I'm going to drop the units on this schematic picture. It's an equilateral triangle of side length 8. We're trying to calculate hydrostatic force. Hydrostatic force depends on depth, right? The force at points that are, say, right there where I'm laser pointing in the triangle is not as much as the force down here, which is not as much as the force down there. So the depth determines the force. So that's why I'm going to coordinatize this problem with a vertical number line. I'm going to draw that. You can draw it anywhere you like. I'm going to draw it right up through the center of the triangle. And that's my coordinate system because the depth depends on, the force depends on the depth. And depth could be measured by a number along a number line like that. I'm going to call it x. The top of the triangle, I'm going to choose to be my coordinate x equals 0, but that's a choice. Yeah, because if I do that, if I pick a certain x value some way down, well, then the depth in the local estimate formula that I'm going to write down will be at depth x. Yeah, so I'm just going to take that thing at depth x. I'm going to give myself a little dx. So if I thicken that rectangle up a little bit, let me just give myself another copy of it. Don't worry about the fact that it's sticking out, right? This is just a Riemann sum estimate. So I'm going to call the thickness of this thing delta x. Yeah, and clearly I can see that its width also depends on x, right? That triangle is not a rectangle. So let me, I don't know where to write it up here, but w of x is the length, the cross-sectional length, the width of that rectangle. Okay, so to make a local estimate, at least I'm going to have to determine what that w of x is, but I'm going to assume, just like we did before, that all points in this rectangle at depth x are at constant depth. Certainly that assumption's false. The points in this rectangle aren't at constant depth, but this is the calculus idea. If delta x is small, that assumption is not going to create a lot of error. Right? If delta x is a very tiny number, then these points in this rectangle, even though their depths are different, they're not very different. So if I assume they're all the same, I won't make much of an error. And I can write down, given this information right now, what my local estimate for the force is. My local estimate Let me draw a line here so it's not so distracting. My local estimate for the force, that is the force on that rectangle, well, how does it work? You have to take your fluid density, that's 840 kilograms per cubic meter. And since that's a mass density, I need to multiply by the acceleration of gravity, right? So that product right there is my weight density, right? The book denotes that weight density variable by delta. I will too, right? And what are its units? That would be newtons per cubic meter. And so I have to multiply that weight density by the volume of fluid pushing on this little rectangle. Well, that volume of fluid, it has a depth x, that's measured in meters. The area of that rectangle is, well, whatever W of x is times delta x, yeah? So in the book's notation here, let me move my label. In the book's notation, this x is our d, and the W of x times dx is our A. That's in meters and meters squared. So you can check that dimensionally, that product is giving us newtons. Newtons per cubic meter times meters squared is newtons. Yeah, and that's kind of giving us the form of this integral. So what do we need to do? We have a couple of jobs that we need to do. We have to determine, well, what is that W of x? And we also need to determine the limits of integration. We didn't say, well, what is the biggest x value over here? Yeah, we have to integrate from 0 to something. So to do that, I'm going to use some similar triangles and also some kind of trigonometry, I guess. So let me sort of outline in a distinct color the triangle that I'm looking at. I'm going to look at half of our equilateral triangle. You can look at the right half if you want to, but I've already started coloring the left half. So I'm just shading this triangle's edges red so you're looking at the same thing I am. It's a right triangle. Its side lengths are, well, 4 and 8. The hypotenuse of that right triangle is 8. And then there's this other side length, which is actually the length that I'm looking for my limit of integration. So how do I find that? Maybe just let me call it h for a second. So let me just write down here that this is x equals h. And then, well, how to find that? I'm not going to put the details in this video. I'm going to leave it to you. But for example, h squared plus 4 squared is 8 squared. That'll do it. You can use the Pythagorean theorem for that right triangle to determine that one unknown leg. Maybe from your geometry class, you remember this is a so-called 30, 60, 90 triangle. So a 30, 60, 90 triangle, there's a relationship between the hypotenuse length and the leg opposite the 60-degree angle. Maybe you remember it that way. I'm just going to put it in here. So I'm not going to do the details here, but this h, if you work it out, stop the video and verify this, it should be 4 times the square root of 3. Okay, so those are going to be our limits of integration, but I still need to find this W of x, but I needed that information to find it. I'm going to zoom out just a little bit so we can still see that picture. This time I'm going to also look at some triangles. Let me color one blue here. Let's see if this pen turns out to be too thick. So one of the triangles I'm going to look at is the black triangle, equilateral triangle, whose side lengths are 8. And then the other one I'm going to look at is this blue one. Okay, so that blue one, its side length is W of x along the top. And side lengths and also heights of similar triangles are in proportion. All right. So what is the height of this blue triangle? Well, on my number line, my x number line, this lowest point is 4 root 3. And this upper point is at x. It's the variable x. So this height is 4 root 3 take away x. So using the principles of similar triangles, I could write something down like, well, W of x, its ratio to that height of that blue triangle, that's 4 root 3 take away x. That has to be the same as the corresponding ratio in the big triangle that's the trough side. So that's the same as the ratio of 8 to our 4 times the square root of 3. So I would stop the video and make sure that makes sense. But if I solve that for w of x, what do we get? Well, we get w of x is 8 over 4 root 3 times the quantity 4 root 3 minus x. And if you distribute that, let me try to zoom a little bit more so we can still see the picture. Distributing the 8 4 root 3 through there, we get what? 8 minus 8 over 4 root 3 times x, and I'm going to reduce that and write that as 2 over root 3x. Okay, so that is our w of x. I'm talking fast, but you can stop the video. But now we are armed with everything we need to write this integral down, right? We have our local estimate. It's written right here, and we just determined what w of x is, and we know our limits of integration. They're going to be 0 to 4 root 3. So I'm going to try to zoom out and keep the picture visible while I write this. So what is the actual force on that object? Well, it's the integral from 0 to 4 root 3. Those are the extreme x values. And then I'm going to write my local estimate, 840 times 9.8. If you have a calculator handy, you could certainly write that out. It's okay with me. Times x times our w of x. Delta x becomes dx in the limit, okay? So that integral, let's zoom out this time so we can look at it in a little bit more detail. If you were going to integrate this, I mean, you'd certainly pull those constants out front. The 840 times the 9.8, you're taking the integral from 0 to 4 root 3. And then if I just distribute that x, it's 8x minus 2 over root 3x squared. So it's an absolutely routine integral. It's a polynomial. So the technique of integration on the integral is not what the issue is here. So I'm actually going to just, to keep this video short, kind of kick the details over to you for that one. But I'll tell you what the answer is. When I worked out this integral, if I can read my own handwriting, I got 526,848. And what would the units on that thing be? We already kind of said that. Sorry for scrolling, but when we talked about our a local estimate up here, we said, well, we're taking newtons per cubic meter and multiplying it by cubic meters, so we're getting the correct units. That's 526,848 newtons. It's the hydrostatic force on one of the ends of that trough. Okay, so I was trying to make comments about the coordinatization of the problem. I hope that's helpful. I'm going to scroll back up to the picture. For given shapes, triangles, rectangles, trapezoids, and so on, I basically like to do this. I like to coordinatize the problem, putting a vertical number line so that the number I'm measuring is the depth. I like the depth equals 0 to be the surface level of the fluid. And then I have to maybe work out what the deepest point on the object is, like we did here. Those are my limits of integration. And then everything was determined by that x variable here. Okay, it's not the only way to coordinatize the problem, it's just one way to do it. All right, let's continue on and look at a second example. Second example, I'm going to kind of contradict myself a little bit here, but again, I think you should stop this and just try to do it. Try to do this problem, but let's check out what it's saying together. So I'm just going to move quickly here, but you can pause anywhere you want. So this time I've got a circular disc. The shape that I'm talking about is a disc. It's submerged vertically in water. This time it's a disc of radius 3 feet. Submerged vertically in water so that the nearest point in the surface is 2 feet below the surface. The picture is drawn. Okay, so you can see the surface of the water up here. I've got my disc submerged vertically. It has radius 3 feet. And the point closest to the surface of the water is 2 feet away from the surface, okay? And the question is, what's the hydrostatic force? What's the hydrostatic force? And why did I say I'm going to contradict myself? Well, this time I'm not going to coordinatize this so that I'm going to put a number line there and think of the surface of the water as x equals 0 and so on, because it will be difficult to describe this circle if the 0 of my coordinate system is up here at the surface of the water. So here's some advice that I have for you. When you're dealing with circles, I like to put the origin of my coordinate system at its center. Why do I like to put the origin at the center? Because that makes the circle easy to describe. easier to describe the circle. You don't have to, no one, if anybody's ever telling you that you have to coordinatize a problem a certain way, they're lying. There's no one way to coordinatize a problem, but there are good ways and less good ways. Okay, so here to save a little bit of time, I've kind of already hand drawn. I'm putting the coordinate system at the center of my circle. And I'm going to call the axes X and Y, even though the depth here is really only going to depend on the Y variable. Okay, and let's kind of try to orient ourselves about where we are here. So if we're putting the coordinate system there, then Y equals 0 is actually right in the middle of that circle. So since the circle has radius 3, the lowest point in this coordinate system is going to be Y equals -3. The highest point in the coordinate system is Y equals 3. And if that point is 2 feet below the surface of the water must have coordinates Y equals 5, right? It's 2 units above 3. And here we're working in feet. Okay, so that's just kind of orienting ourselves. And then let's take a cross section. I think I'm going to draw one so that it meets that radius right there. That's a cross section at level Y. So I'm choosing kind of a variable Y. And again, I'm going to thicken it. I'm going to thicken that cross section, ignoring the error that I'm making. I'm going to assume that all points in this rectangle are at the same depth. That depth is not Y. We'll think about that in a second, but I'm going to assume that all points in that rectangle are at the same depth, and in particular, the thickness of that rectangle, I'm calling it delta Y. Okay? We're going to need to know how wide it is. It also has a width that depends on Y. Okay? So just like the last problem, when the shape isn't a rectangle, the width varies, and that width varies with respect to the variable that we're going to integrate. But we can already start writing down a local estimate given what we have here. So assuming that all points in that shaded rectangle are at the same depth, then a local estimate for our force would be what? Well, you have to take the weight density of water. I didn't write it in this problem, but throughout the entire section, we're assuming that the weight density of water is 62.5 pounds per cubic foot. Okay, so that's the constant that we're going to use for the weight density of water. And then I need to multiply that by the depth. Well, how deep is this segment? How deep is this segment Y? Well, the depth is the distance to the surface of the water, but that's not equal to Y, right? You got to stop the video and think about that. But we've talked about this a lot: inner and outer radii, shell radii, the previous problem. This coordinate down here is Y. The coordinate at the top is Y equals 5, right? You can see in the coordinate system that Y equals 5 is bigger than Y. So the depth of the top edge, and hence I'm assuming all points of that rectangle, is what? You take the bigger coordinate minus the smaller coordinate. So it's going to be 5 minus Y, right? So that's our depth in feet. If I put in the book's notation, the 62.5 is like the delta, D is like the depth, and now I need the area, right? So that's the fundamental principle. Force is weight density times depth times area, if everything is constant. So we're doing this local estimate. What's the area? Well, I can write it in here, at least in terms of that width function. It's going to be W of Y delta Y. Okay, so what do we have to do? We have to find W of Y. Well, you could use the equation of the circle, right? So the equation of this circle is x squared plus y squared is equal to 9. That's one of the benefits of putting the origin of the circle at the origin of our coordinate system at the center of the circle. So I can definitely see that this w of y, well, what do I want to do? I just want that length. Sorry, I can't find my laser pointer. I want to know this length. Well, that length is certainly twice the x coordinate of a point on this circle. If I label this point right there, x comma y, right? So that's just motivating me to take this equation and say, well, x is, I'm going to take the positive square root of 9 minus y squared. And so I can see in my picture that w of y is 2 of those. Okay, w of y is 2 of those. Why is that? Because this x coordinate that I wrote down, that's this length, right? The x coordinate is the distance from the y-axis. Well, w of y is that plus the other side. That's why I've doubled it. All right? So we can drop that into our local estimate above. We got 62.5 times 5 minus y times this thing we just found, 2 times 9 minus y squared, delta y. That's our local estimate. What are our limits of integration? Well, what range does y go between for points in this surface? The lowest value of y is down here at -3. The biggest value is up here at +3. So this local estimate is valid, if you like, for y between -3 and 3. And that should be enough information for us to write the integral down. All right, so let's do it. So the force is the integral from -3 to 3, and I'm just writing my local estimate. 62.5 times 5 minus y times 2 times the square root of 9 minus y squared, and in the integral, delta y becomes the infinitesimal differential dy. Okay, so that's using the coordinate system for circles. I always like to put the center at the origin. And now let's kind of see how we might go about integrating this thing. So first of all, the 62.5 gets multiplied by 2, and that's a constant. We can put that out front. 62.5 times 2 is 125. Even I don't need a calculator for that, so I'm going to go ahead and write that. 125 times the integral from -3 to 3. And then I've got 5 minus y times the square root of 9 minus y squared. Kind of like in previous examples, this integral, I'm going to split it up. I'm going to split it up because of this difference. Okay, so I'm going to do some algebra here on the fly. So I'm going to leave my 125 out front. And then I'm going to take the integral from -3 to 3 of 5 times that square root. Okay, that's dy. And then I'm going to subtract the integral from -3 to 3 of y times that square root. So those are the integrals that we have to compute. And just like in our, I think it was the last day of trig sub, we want to handle those things separately. We want to compute those integrals separately. So if you want to proceed with techniques of integration, then you could do this one with trigonometric substitution, right? It's got a square root of 9 minus y squared in there and no other terms. The 5 is a constant. You can certainly put it out front. Maybe this is going to make it harder to take notes from this video, but I'm going to take advantage of my iPad here and just put the 5 out front right now. All right, so now you know why it's out there. And then this one over here, I wouldn't use trigonometric substitution. You can use an ordinary substitution, right? Because the derivative of 9 minus y squared up to a constant is in the it's y dy. It's -2y dy, but the constant won't stop you. So good. I would see if you can carry that out, carry those things out. I'm going to mention here something because I can see it. It's not always the case, but in this particular case, there's an easier way to calculate these integrals. Namely, if I, just to highlight here, if I think about what this integral is, the integral from -3 to 3 of the square root of 9 minus y squared, well, we've already said above, the square root of 9 minus y squared is the semicircle, graph of a semicircle of radius 3. And if you're integrating that from -3 to 3, you're just taking the area of that semicircle. So another way to see what this thing is, this is the area, this integral, and not including the 5. So it's the area of a semicircle, half a circle, I mean, with radius equal to 3. Okay, well, a circle of radius 3 has area 9 pi, right? 3 squared times 5. If you want the semicircle, you just take half that. So I'm not doing that integral by integration. It's faster than the trig sub. It's very special because it's a circle, some area I know from geometry, but I can take advantage of that. I'm going to take advantage of something over here too. Y times the square root of 9 minus y squared is an odd function, right? I mean, when you integrate an odd function from minus something to something, you get 0 because of the symmetry of the odd function. So it's an odd function integrated over a symmetric interval. So that's going to just turn out to be 0. You can check it when you do your ordinary U substitution. I think it would be a good thing for you to do. Okay, so I'll just leave it to you to check the arithmetic, but if you multiply out 125 times 5 times 9 times pi, and you divide it all by 2, I wrote it down, you should get 5,625 times pi all over 2, or if you want to the nearest whole number, that's about 8,836. And then what would the units be? This is force, where we were measuring in things in feet, so our units is pounds. So the force on that circular disc is just under 9,000 pounds, right? That's the force exerted on the disc by the fluid itself, hydrostatic force. Okay, one more example. I'm talking fast. You should stop the video and take a drink of water or something, but one more example. This is actually one of your homework problems, number 6 in section 8.3. So I'm not going to compute it all the way. But I do want to just sort of speak about how to coordinatize it. And again, I think you should stop the video and kind of ask yourself, can you do it? I bet you can finish this problem before you look at the rest of mine. But here we want to find the hydrostatic force on the surface shown. It's a semicircle. It's a semicircle. Its diameter is 12 meters. But this semicircle is not completely underwater, right? Only 4 meters of it is underwater. So I would recommend you put the coordinate system's origin at the center of the circle. Stop the video and see if you can't just work it out. Work out your local estimate, okay? So here, I've got this pre-drawn. I'm not going to calculate the integral, but I'm going to take my own advice, and I'm putting a coordinate system so that its center is at the origin of it is at the center of this circle, okay? Circle has radius 6 because its diameter is 12. And then I'm going to, just like we did before, take a slice at some level y, right? We already worked this out above, so I'm going to be pretty quick about this, but the width of that thing that I just drew, well, what would it be? It would be 2 times the square root. In this case, 6 squared is 36 minus y squared. So I'm going a little bit faster here, but the example above shows you why that's true. Yeah, so we can write down, I'm not even going to write the local estimate this time. The force should be the integral of, well, here we're working in meters. So the weight density of water is 9,800 newtons per cubic meter. What is the depth of this segment that I drew up here, right? So this is my segment, and I'm wondering what its depth is. So, well, what is the y value at the top of the circle here? If y equals 0 is the bottom edge of the semicircle, then the top edge of it must be y equals 4. I've already drawn it on there, right? So what is the depth? The depth is the difference, 4 minus y. 4 is bigger than y. Okay, so that's your depth. What's the area? The area is the width, dy. What are the limits of integration? Lowest point on the surface is at y equals 0. Highest point on the surface is y equals 4. Okay, so proceeding exactly like we did above, I'm going to write the 9,800 times 2 out front, and I'm going to split this integral. It's going to be the integral from 0 to 4 of 4 times the square root of the 36 minus y squared dy. Take away the integral from 0 to 4 of y times 36 minus y squared. Okay, and then the last thing I'm going to say in this video is that symmetry and geometry that I used above does not apply here, right? Because yes, this is still the graph of a semicircle, but you're not integrating it from -6 to 6, so that's not going to be the area. So you really need the trig sub here. So in case I caused you to lose faith in knowing these methods, if you want to know that number, you got to do that integral with trig sub. You're going to let y equal 6 times the sine of theta and proceed. Same thing here. This integral is not 0, right? Y times the square root of 36 minus y squared is still an odd function, but that integral is not 0 because you're not integrating it from over a symmetric interval. You're not integrating it from -4 to 4. You're integrating it from 0 to 4. So you need to do the u sub. Okay? But I'm not going to do it here because that would be wrong. That would be stealing one of your homework problems from you. And that is not something that I would ever do. Okay, so I hope that these were useful illustrations of how to coordinatize at least these problems. And then you can maybe come back here and look at these ideas as you're trying to coordinatize the problems that I've asked you to do in the text. Thanks for listening.